Welcome back, differentials and linearization. We're going to talk about linearization in this third installment. I broke this up into shorter videos than two big long ones. The differential we looked at in the last section gave us a linear approximation. Well, if that be the case, instead of just using it to find one linear approximation, why don't we figure out what the function is? And the function ends up being a plane. It ends up being a tangent plane. Later on in the semester, we'll talk about tangent planes, and we'll see it's just this all over again. This is just a different name for it. Here's a linearization formula. It's going to be a function of x, y. It's f of x0, y0 is the starting point, plus this is nothing more than the differential, df. Pick some xy value, you substitute, that's dx, that's dy, and there's the partials in front. I chose to use this Euler notation instead of the Leibniz notation. It doesn't really matter. You can put partial of f with respect to x, partial symbol f with respect to y if you want. It's the same formula. So let's return to this elliptic paraboloid. Let's see if we can find the linearization at 2, 3, f of 2, 3. We need to simply plug into this formula, and the answer is going to be a function. Well, first of all, we need f of 2, 3 here. F of 2, 3 is simply 2 squared plus 2 times 3 squared, and that's 18, that's 22. Okay, that number should look familiar. That's what we had in the last example. And in this case, x0, y0 is 2, 3. That's our starting point. That gives us a lot. A 2 goes in here and a 3 goes in here. And now we have to find these coefficients by finding partial derivatives. Let me find the partial derivatives over here. And fx is equal to 2x. fx at 2, 3 is simply 4. Plug in 2 here. 2 times 2 is 4. Fy, f sub y is equal to 4y. The constant term goes away. Fy at 2, 3 is equal to 4 times 3, or 12. So let's see, we have a 4. 4 goes in here. 12 goes in here. And 22 goes in here, and that's going to be our linearization. L of xy is equal to 22 plus 4 times x minus 2 plus 12 times y minus 3. And you could leave it like that, or if you want, you can multiply it out and simplify it. But this is a plane. You could call this z. Z is equal to, let's see, negative 6, negative 8, negative 14, plus that is 8. This is really the same as the plane z equals 8 plus 4x plus 12y. That's exactly what it is. It's a plane that happens to be tangent to the surface. And that is a plane equation that you may recognize from before. Now, we're not finished with this example. Let's go back to this form of the linearization. And let's suppose we want to find L of 2.1, 3.1. Makes it easier in this form. You end up with 22 plus 4, 2.1 minus 2, plus 12, 3.1 minus 3. Okay, 2.1 minus 2 is 0.1, 4 times 0.1 is 0.4, so you get 22 plus 0.4, plus 0.1 times 12 is 1.2. what does 0.4 and 1.2 look like? That's 1.6. That's how much it changes from this starting point. And we end up with 23.6. So it's the same material that we did before, except for now we have a function you can plug into instead of redoing things. If you wanted to know what would happen if we changed x by 0.01, change y by negative 0.2, or if we want to know what's happening at a specific location, like 1.9, 3.24, you just substitute. We've functionalized this. So, okay, that's all for linearization and problem set 7.